Hey there, my name is Ben Rodney from ASHRAE New York, and I want to welcome you to this episode of the ASHRAE New York Designer Series and the brand new ASHRAE New York YouTube channel. We'll be bringing you educational content, interviews, and chapter updates, and it'll be open to members and non-members alike, or anyone just interested in the HVAC industry or updates on our chapter. You can find us on LinkedIn, Instagram, and make sure to go to our website, ashraeny.org, where you can sign up for our newsletter, check up on chapter events, and hopefully even join us as a new member of the chapter. If you like what you see here, make sure to hit the subscribe button below this video and then hit the bell to get notifications on any future updates to the channel. If you have any comments, questions, or conversation about this video, just leave them in the comments section. Thank you and enjoy the episode. Good afternoon, everybody. My name is Ben Rodney from ASHRAE New York, and I want to welcome you to episode 5 of the ASHRAE New York Designer Series. These have been a great success, and we really appreciate everybody's support of this program. This is our largest attendance yet. We had over 66 people register, so we think it's going to be a great topic. I'm really happy to have our new friend Steve Sadowski from Loring Engineers to present an excellent presentation on fan fundamentals. We think this will be good for beginner engineers or anyone that just wants to brush up on the basics of fan fundamentals. So you can see on your screen, I just wanted to talk about our upcoming programming and some of the ways that we advertise our chapters. So next week's designer series, we're going to have Anthony York from Cisco presenting on disaster preparedness and case studies. He's put together an excellent presentation that's been presented at ASHRAE national conferences with some updates for COVID. And then we also have some partnership programming coming up in June with the Building Energy Exchange. So that's going to be a great program on optimizing HVAC for health and efficiency with some specific issues dealing with COVID. And we also have some programs coming up with our Cross Learning Alliance with Urban Green and AIA, which are not on our website yet, but as soon as those dates are up and the topics selected, it will be up on our website, ashraeny.org, so make sure you visit there to see what the upcoming events are. You can check us out on Instagram, LinkedIn, and make sure to visit our new YouTube channel. Just search for ASHRAE New York. This presentation will be posted to that channel a few days after the event, so make sure you check that out. In terms of this presentation specifically, we're going to be doing a Q&A at the end, so make sure if you have any questions, you put them in the questions bar on your GoToMeeting interface there, and then we'll ask them of Steve at the end, so probably about 10 minutes for questions. This is worth 1 PH credit. It's accredited with the Practicing Institute of Engineering. So make sure after the presentation is over, you fill out the survey at the end. That gives us all the information we need to present to I, and we'll make sure that you get your certificate tonight or tomorrow in your email. And just make sure to turn off your pop-up blockers because we had some issues with the survey not coming up if you have the pop-up blocker on. So I'm going to throw it over to Steve to teach us about fan fundamentals.
Hey, great. Thanks, Ben. Appreciate it. Hi, everybody. How you doing? Like Ben said, my name is Steve Sadowski. Hope everybody is maintaining some level of normalcy here and staying safe and healthy during these certainly unusual times. As Ben said, I'm a senior associate with Loring Engineers. I've been doing this for about 13 years now, and I've been with Loring since 2018. Today, we're going to be taking a look at fundamentals of fans. Fans, as I'm pretty sure everybody knows, are one of the most common pieces of equipment that we see in mechanical systems. Whether they're operating by themselves or a standalone item or a sub-assembly of a larger piece of equipment like an air handling rooftop unit. If you have any kind of HVAC systems, chances are pretty good you're going to have a fan. And you know, it's not even just airside systems. When you look at hydronic systems and their equipment, you're going to find a fan in there somewhere too. Boilers, for sure, if they're forced draft, there's going to be a fan in there to create that draft. You know, sometimes you'll see a fan in the breaching, again, for draft. So it's a little bit different application than what we're going to talk about today, but just to give you a broad spectrum of where you can find fans. So pretty much everywhere, right? So with that being said, what are some common points with respect to fans and the way we apply them to HVAC systems? So HVAC fans and blowers are used to move air through the HVAC system. Either you're going to exhaust, supply, outside air, relief, pretty much any HVAC, airside systems. Again, you're going to have a fan. So the fan spins a blower and turns it by means of an electric motor, creating directional airflow. Fans are an integral part of air handling systems for different applications, different types of systems, different service. Fans and blowers can be mounted in different configurations. They can be mounted at the exterior wall. They can be above ceiling inline fans, on the floor, base fan, on a roof, on a curb. They can be used for air handling systems, ventilation systems, kitchen hoses, pretty much, again, anything. Fan drives, belt driven, where you have a belt, sheaves on the end of a shaft to turn the fan off the motor, or it can be direct drive, where the motor is physically attached to the fan wheel itself. You can have single fans, just standalone by itself. You can have a fan array, which we're going to see a little bit later. Fans, again, used now with the energy efficiency requirements, typically seeing VFDs or variable frequency drive to control the speed of the fans. And as energy codes get stricter, that's definitely becoming commonplace. I'm sure you've seen single zone VAV systems. Also, things like kitchen systems now are also variable speed, and laboratory hoods, garage exhaust systems. And most common HVAC fans are made of carbon steel, aluminum housing, and your components as well. Stainless steel and plastic and other material can be used for specific applications that are a little outside the normal window, where may be facing some corrosive materials or corrosive air streams, and that helps protect the fan configuration and the wheels and components being eaten away. So when it comes to fans, we have numerous tools that are available to the design engineer to help us specify and interpret the data. These can be applied when looking at the data in fan selections, submittals, testing and balance, and they're even doing troubleshooting in the field. We have airflow readings that are too high or too low. So one of the first things we can look at are the fan affinity laws, or commonly just known as fan laws. These fan laws, they offer a way to relate performance of a fan in a specific condition to a changing system variable. So as you can see, there are three common equations: fan flow, rotational speed, and fan pressure, as well as these are based on the fixed fan wheel diameter. So we're using the same fan. The fan itself isn't changing, but we're changing some of these different parameters because of system changes or use changes, right? We need additional airflow somewhere in the system, or if our static pressure is higher than what we thought it would be. So fan airflow and fan speed and RPM from fan law number one, you can see are directly related, right? It's just a ratio of CFM to the RPM. So fan law number two is relating the static pressure to the fan RPM, but the RPM is related via the square of static pressure, and horsepower similarly in the cube of RPM. So to provide a little summary, if the fan speed is increased by 50%, your new airflow is 50% of the original airflow, because again, it's a direct relationship. The pressure would be 25% of the original pressure, and the new horsepower would be 12.5% of the original horsepower. And similarly, if the price is increased, in this case by 25%, new airflow, 125% of the original airflow, the new pressure, 56% of the original pressure, and the operating horsepower, 25% of the original horsepower. There's also ways to relate these parameters when you have a changing wheel diameter. These are presented here. It's relating the fan speed, the air quantity, the fan power, and then the static pressure. But now you're introducing another component, which is the diameter of the fan wheel. And you can see, the diameter of the fan wheel is just an additional term in the equation, all the way to the right there. So if we look at an application of the fan laws, let's say we have a project that we're designing right now, and we're looking at specifying a fan for part of the air distribution system. We've done all our load calcs, we've done our static pressure calcs, and our ventilation calculations, and So we've come to find that we need a 10,000 CFM fan operating at 1.5 inches of static pressure. So we've used a computerized selection program from the manufacturer, from any fan manufacturer, or we've selection from a representative, and we've got the following fan selection here. So we see that this particular fan is going to provide a 10,000 CFM. It's going to provide 1.5 inches of pressure. The fan's going to be operating at 1,034 RPM, and the brake horsepower is going to be 4.59 horsepower. Let's get during construction, because we all know this never happens, right? So during construction, we get an additional office space into the ventilation. We find out 20% more air, and then everything is already installed. So how can we see it in the task? Well, we can go back to our fan laws. So we know that UCSM is 20% more.
Hey, Steve, it's Ben. I'm sorry to cut you off for a second. Would you be able to make sure to, if you're on a speakerphone or your cell phone, just make sure it's you're consistent with where it stays, or if it's remounted or something? We're getting a little feedback on the audio, little issues with the audio.
Yeah, sure. I'm sorry. I'm actually using a set of earbuds, and so I'll try to hold that straight if I can. Apologize. Okay. So anyway, so we know that we need an additional 20% of air. Right? So 10,000 CFM, 20% more air would be 12,000 CFM. So going back to our fan laws, we can obtain a new fan RPM for that airflow rating. So we see that the new RPM would be 1,241 RPM. Similarly, the static pressure is also going to change as a result of the fan law. We see that our new static pressure is now 2.16 inches, and our new brake horsepower has also changed. It's gone from 4.59 to 7.93. So in order to get 12,000 CFM from the original fan, we have to increase the fan speed from 1,034 RPM to 1,221 RPM. And in this case, we're also going to have to change the motor. If we look at the original selection, we had a 5 horsepower motor selected. Now our new brake horsepower is 7.93 for this particular fan at this particular operating point, and we need to increase it to 10. So the fan can certainly do it in this case, but it's going to require a little change Now, this may not always be possible, depending on particular fan selected and its construction. But in this case, it can. It's going to depend on the type of fan that was selected. And
hey, Steve, we're still having some issues with the audio. Is it maybe just go to speakerphone, or just?
Sure, let me give that a shot. Is that any better?
Yeah, we'll see. All right, thanks a lot.
Sure, no problem. So when we're talking about fans and what we get with them, oftentimes we'll see discussions about fan curves and system curves. So fan curves are a function of the fan itself. They relate primary variables of fan operation. They're commonly presented as a relationship between the airflow and pressure for a fixed wheel speed and diameter and a constant air density. They're generated in accordance with fan testing that is performed in accordance with AMCA 210. That describes the methodology needed by the fan manufacturers to create these fan curves. And they're specific for each fan model configuration. You're not going to have 2 fans with the exact same fan curve. Now, the system curves, they're curves related to the property directly of our air distribution system. They're the relationship between airflow and static pressure at a fixed set of parameters and created using the fan law equations we just looked at. So a new system curve is going to be created when one of these properties change in our system. So here we just have a example of what you might typically see in a fan curve. You have your various RPM fan speed curves, fan speed here. So there's a curve for each fan RPM across the operating range of the fan. Again, these are generated in accordance with testing that's done in the lab. We also have here, which you'll typically see as typically known as the do not select curve. So when you get to the left of this curve in this region over here, you'll find that the fan operation becomes unstable. It's not ideal to select to the left of that curve because the fan may operate unpredictably. You may get some surging, you may have some vibration. So typically manufacturers and practice will tell you to stay to the right of that curve. Now we also have the system curve. So the system curve, again, is a relationship to the system airflow versus the system static pressure. And we generate these from our operating point, but also create additional points using our fan laws. And if we have a parameter change, whether it's CFM or static pressure, we're going to have a point that's no longer on this curve. So therefore, we'll be generating a new curve for the new system. So we can take a look at an example here of how we generate the system curve. So let's go back to our previous example where we had the 10,000 CFM fan at 1.5 inches of static pressure. So our design condition is, again, 10,000 CFM, 1.5 inches. So how do we get these other points on the curve? So in this case, we can determine the curve. Let's plot a new point, CFM versus static pressure. And we can use our fan laws to find what that static pressure is going to be at those CFMs. So that's the orange point here on this graph is our design point, and the green points are what develop the curve, and those are created based on the fan laws. So let's overlay our system curve and our fan curve and see how the two interact. So the operating point of the fan is going to exist where the system curve and the fan curves intersect. So we can see at the 10,000 CFM and at 1.5 inches of static pressure, our fan's going to be operating at 1,034 RPM. You can see we're pretty far away from our do not select curve, which is a good thing. And our operating speed, it's not really max. It's not really at the minimum of the fan. We're kind of right in the middle of the fan operating range. So we do have a little flexibility in this fan. So let's see what happens if we have a problem in the field where our system curve changes, or again, maybe there's an additional airflow that's required. So how does that affect the way these curves interact? So in this case, we can see our project's almost done. Our systems are all started, they're running, we're getting the testing and balancing reports in, and we're going through the rest of the systems. Everything looks good, and then we get to our sample fan. So we needed 10,000 CFM, but when the developer sets our fan to 10,000 or 1,034 RPM, we're only getting about 9,000 CFM now. So what happened? What happened here? Why come we're only getting 9,000 CFM? So due to some changes, whether it's in the field, maybe additional elbows or offsets needs to be added to get around piping or a beam or something to that effect. We've now kind of ridden up the fan curve at the given RPM. So we have an increase in system resistance, which is called reduction in airflow. So in this case, the blue line is our original system curve, and the green line with the orange point is actually now our new system curve. That's where our fan is currently operating at. So how do we get back to our 10,000 CFM and get back on track with our fan here? That's kind of gone a little away from our design values. So we need to find an RPM that corresponds to the changes that have been made in the system. So using the fan laws, we can relate the design airflow to the actual airflow, and we see that we come up with 1,149 RPM. So the 1,149 RPM would be our increased resistance in the system. The new static pressure that we're going to develop is going to go now to 2.346 inches, and our brake horsepower as a result is also going to increase. It's going to go from 4.59 to 6.3 brake horsepower. So now we're operating on our new system curves. And again, we have an increase in static pressure, we have an increase in fan RPM, and we also have an increase in horsepower. So going back to our original fan selection, which we had a 5 horsepower motor, now we're up to 6.3 brake horsepower, and again, now we need a motor change. So in hindsight, one thing to keep in mind is if you're going to be near the actual motor, rated motor horsepower, we should probably leave yourself a little leeway in that. So a 4.6 brake horsepower fan probably would have been a good idea to go with a 7.5 horsepower motor right from the start, because now at this point, in this example, our fan's installed, our VFD is installed, our wiring is hooked up, and a change from a 5 horsepower motor to a 7.5 horsepower motor might require some of those other components to be changed as well. So probably more cost effective to leave yourself a little flexibility in your fan motor horsepower in case you run into something like this, which isn't all that uncommon. So now we got a little background on fans and the fan curves and some of the principle behind that. Let's take a look at some of the codes and standards that could be applicable to fan selections and applications. So right up top, we have our applicable building codes. We certainly have to look at the building codes and the mechanical codes when we're talking about fans. These will provide guidance, things like fan termination locations, clearances, and certain aspects of fan construction. For instance, kitchen hood exhaust. There are some specific construction requirements that are outlined in the code that would be applicable to that type of exhaust system. So that's all part of the building codes and the mechanical codes. Energy codes are going to provide us guidance for controllability of the fan as well as the system efficiency. UL 705 is going to tell us about the electrical wiring of the fan and safety requirements associated with that. Our AMCA standards are going to provide guidelines for design, application, troubleshooting, and measurement of fans and systems. And there are also some additional AMCA standards that are going to be for associated ancillary equipment, so things like louvers, dampers, fire smoke dampers, and fans in different applications like process and power generation. We also have AMCA standards. In addition, something's not listed here, we also have UL 762 for restaurant applications. We have the American Conference of Government Industrial Hygienists Industrial Ventilation Handbook, which is good for industrial applications or process applications. And we also have SMACMA, which provides some guidelines as well when it comes to duct design and other things associated with fans. In addition, we also have some NFPA codes, which are applicable to fan construction. NFPA 45 with respect to spark resistant construction and laboratories using chemicals. NFPA 96 for cooking equipment. And NFPA 91 for fans for hazardous materials and the chemical and physical properties that are associated with those specific materials. NFPA 90A, which is the general requirements for installation of HVAC systems. NFPA 92, smoke control. And one point to note is that fans used for smoke exhaust systems must comply with UL 705 as well. And of course, one reference to always have is the ASHRAE handbooks. A lot of good information in there with respect to fan construction, fan application, fan design. So always a good go-to resource for anything related to fans. So how about fan types? There's no real one-size-fits-all application when it comes to fans. Different applications are going to require a different type of fan, different location of fan, depending on the service, the building, noise requirements, performance requirements. So what types of fans do we have at our disposal to help us get our designs in line? So number one, we have centrifugal fans, which are probably the most common and widely used fan that we see in general HVAC applications. They create pressure and air movement by a combination of centrifugal velocity and rotating velocity, and air is discharged perpendicular to the shaft of the fan. Fan characteristics of a centrifugal fan and capacity performance can be changed by changing the shape of the blade, speed, and the diameter of the fan wheel itself. And just down the bottom here, we have a couple different images of a typical utility set fan on the bottom left, and just a animation of the rotation of the fan wheel and the discharge and inlet patterns, and a CFD diagram showing the profile of the air as it enters and leaves typical centrifugal fan. So there are three major classifications of centrifugal fan wheels based on blade shape. Those are common ones are airfoil, backward inclined, or forward curved. So forward curved fans have relatively low tip speed, and the tip speed is the speed of the tip of the fan wheel measured in feet per minute. These fans are relatively quiet in application, and they're generally used for producing high volumes of air. They're low cost, and again, these are common fans that we see in HVAC applications. Another type is airfoil blades, which would be shape of the blade would look like letter D, the diagram over there. These have the best mechanical efficiency and lowest noise levels of centrifugal fans, primarily used for clean air applications, but they are a little bit more costly compared to the other types of fans. And we also have backward inclined or backward curved fan blades. Performance of these is similar to an airfoil, but the peak efficiency slightly lower, and they're a little bit less costly to procure. Next up, we have roof ventilators, which are a type of centrifugal fan. Pretty much, I'm sure everybody's seen at least one of these in their lifetime. There's several different types, and their application is very broad. They could be applied to different types of ventilation systems, whether it's general exhaust, like toilet exhaust, environmental air, relief air. They can also be applied to kitchen exhaust if you're using a upblast fan that's rated for the application. Supply air can also be provided. Sometimes for kitchen makeup air, you'll see one of these guys if it's a smaller application, and relief air as well. And these are just a couple of the applications that roof exhaust fans can use. So the fan, if you have a fan on the roof, it's going to be mounted either directly on the roof on a roof curb. Exhaust or supply roof ventilators can be subdivided in a couple of ways. We have upblast fans or downblast fans. So upblast, the discharge of the air is vertically up, and downblast, the air is going down. We have axial flow. We also have centrifugal. Roof fans can also be direct drive or belt drive. Direct drive fans are becoming much more common, again, with respect to energy, but also with maintenance. If you look at it from a maintenance perspective, direct drive fan is much easier to maintain. You always have to feel bad for the person who has to go up onto the roof in the middle of winter when it's snowing or raining because the fan belt broke. And direct drive fans can kind of take that out of the equation. So you don't have to worry about belts or pulleys or sheaves, and they're inherently more efficient because you don't have any drive losses. Your motor's directly on the end of the shaft, which is good. So the most common material for rooftop fan housing and the fan blades themselves is aluminum, but there are options. So an upblast fan is required usually by code for the exhaust of grease-laden air from the type 1 kitchen hood, because of the accumulation of grease on the roof would create a fire hazard. So in that instance, you would not want to apply a downblast fan to a kitchen exhaust system, because instead of your grease-laden air being dispersed up into the atmosphere and having the ability to be distributed, or absorbed via the wind, and it would just be dumping right on your roof, which wouldn't be a good thing. And also, going back to the mechanical codes, right, we have a limit on the discharge of the kitchen hood where it has to be a certain height above the roof anyway. So a downblast fan wouldn't really be seen in the kitchen exhaust application. An upblast fan can also be preferred for some machine shops or foundries and other work where you have particulate in the air, oil, dust, anything that you wouldn't want just dumping onto the roof, or in the you'd want it to be carried away from people who may be working on the roof. You wouldn't want that just coming out, dumping on the roof and blowing in everybody's face. That wouldn't be good. Radial discharge and upblast fan can only be used for exhaust, but fans used to supply air are downflow type fan. but downflow can also be used for exhaust. We can use that for general exhaust, toilet exhaust, any of those types of applications. There's also a special type of roof fan can be used for laboratory exhaust. This is known as a mixed flow type, and specifically designed for mixing laboratory fumes and bypass outside air. And there's a special Venturi hood at the exit of the fan nozzle, which discharges the air as high as 200 feet with an entrainment ratio of 50:1. So these could be used in applications where you really want the air, the outlet of the exhaust to be dispersed away from the roof or the building, because of, again, for laboratory applications, you may have some chemicals, you may have some not so good things that you don't want to be discharging in the direction of people or where people can be affected by them. So these fans, you're going to have your air come in from the bottom, your exhaust air, and then you're going to induce air in through the other openings, and you're going to have a high outlet velocity, which is going to throw that air up and away from your building. So next up, we have inline fans. Inline fans are, again, a very common type of fan that you'll see in just about any application. Typically installed in the ductwork, whether it's on the inlet, the discharge, or both. They can be provided with duct flanges on both ends, and they can be used to pretty much any general application. They could be belt drive or direct drive as well. Typically, if it's a direct drive, again, the motor is located within the fan housing, and it's directly on the end of the shaft. The fan shown in the bottom right there, that would be a belt drive fan. You can see the motor sitting on top, and the belt is just beyond the blue motor there. You can kind of see it going down into the enclosure. So on the end of that motor, you'll have a pulley. On the end of the fan wheel, you'll have a pulley, and the belt is what connects the two items. Most widely used where a fan needs to be installed in an occupied space or in a storage room. They come in different shapes, different profiles. There are some low-profile fans where you don't have a lot of ceiling space, and there's also some high CFM fans where they can get rather large. So, but if you have to install it inside, typically a good application. And these fans, in the grand scheme of things, are usually small and in terms of CFM and relatively low static pressure. Because again, if the footprint or the physical dimensions are kind of limited, especially if you don't have a lot of space in the building. So we also have plug fans or plenum fans. It's a different type of centrifugal fan. It does not have a scroll casing and is operated in a plenum by pressurizing the plenum itself to push the air out. Most of these fans are used in a fan array application with multiple fans located within one air handling unit, and they're also used in smaller units where you don't have the space for a traditional forward curved, backward inclined airfoil, house type of fan. A plug-and fan arrangement gives you some flexibility in terms of the discharge duct connection, because the discharge air plenum is pressurized. So you can have, your discharge doesn't have to be right at the outlet of the fan. It could be in the top of the casing, the end of the casing, the sides, etc. Fan walls are also where you will see these, are fan arrays. They're becoming very popular because with the advent of direct drive motors and ECM motors, they give you a lot of levels of redundancy. So in an AHU, you might have 6, 8 fans that are all supply fans, and they're all providing a portion of the total supply air. And these are good in applications where you need some redundancy. If you had a unit that had one fan in it and you lost that fan in a critical application, let's say a hospital or a higher education laboratory where you needed to have that supply airflow constantly. If you lose a fan, that's a big problem, right? You can't shut down an operating room or you can't shut down a hospital. So what you can do in a lot of cases is have multiple fans. If you lose one fan, you can still run the unit with the remaining fans. So let's take a look at. Here's an example of that. These are fan arrays, and you can see you have an array of a lot of little fans instead of one big fan. So if you lost one of those little fans, you may have to run the unit at a reduced airflow, but you're still going to have airflow. You're not going to have all or nothing. So again, these are really good in applications where you need some level of backup or some level of redundancy. And again, being direct drive, they're also rather efficient. And depending on how they're wired, you could have one VFD controlling all of them. You could have multiple VFDs, multiple drives. So there's a lot of options even with the controls as to how they're controlled, and you can get integral airflow measuring stations. So they're pretty they're gaining popularity. Pretty much every major air handling unit manufacturer is going to offer something like this. So our next type of fan that we have, we do have axial fans. So as the name indicates, the air is going to move along the axis or parallel to the fan shaft and not radial. These fans may be vane axial or tube axial. Tube axial is essentially a propeller fan that's located within the housing. Vane axial is very similar, except it has straightening vanes, which provide a little bit better performance. These types of fans you'll see, they'll move high volume of air, but it'll be at a relatively low to moderate static pressure. And these fans are also, like an inline fan, installed within the ductwork itself or in line with the ductwork. And again, you can see the flanges that are provided on the end of each fan. You bolt your ductwork or your flexible connection right up to that. Propeller fans are similar, or a type of the axial fans are a type of propeller fan. Again, in this case, the propeller fan is just mounted individually to the wall. These are common for mechanical room exhaust, where you just kind of attach a fan to a louver, or where you need some just local exhausts. I'm sure we've all walked into older buildings where they put in a kitchen, and instead of doing a proper kitchen design with makeup air and ventilation, they just slap one of these in a window and call it a day. Now, that's not the right way to do it, obviously, but that's certainly an application for these fans where you just need volumes of air moved with no pressure drop and relatively easy. So these can be used in, again, mechanical rooms, local exhaust, ceiling fans, cooling towers, condensing units, where you're just pulling air through coils or through cooling tower fill. And again, they move high volumes of air, but they really don't have the ability to develop a lot of static pressure. And if you've ever been in a room with one of these fans, you'll know that they're typically pretty noisy because there's no any type of attenuation. You're hearing all the air noise and the motor noise, and they're generally low efficiency. So there are applications out there for these, but probably a little less common than some of the others. All right, so we also have a mixed flow fan. Mixed flow wheel is a hybrid. It's a hybrid between an axial propeller and a centrifugal fan. The result combines the best axial and centrifugal fan properties. These fans are highly efficient, and they have increased pressure capabilities, relatively low sound levels, and a steep fan performance curve. So to further enhance the fan's performance, straightening vanes are typically provided in the housing, and they convert swirling air into a straight axial flow, which results in a static pressure rise and good energy savings. So again, these fans are installed in line with the ductwork. If correctly designed, they'll have a stable fan curve without any stall or unstable operating point. They're non-overloading and a flat horsepower curve. And again, these fans are relatively quiet, lowest of any inline fan. So when we're looking at fans, we also have some important terminology that represents itself. You'll see in specifications or manufacturer data or submittals. Some of these include the fan class, fan arrangement, SWSI, which stands for single width, single inlet, and DWDI, which stands for double width, double inlet. The system effect, and sometimes you'll see CFM presented with a little letter in front of it. So SCFM or standard CFM, and ACFM, which would be the actual CFM. But we'll talk about that in a little bit. So the fan classification is going to be based on the fan performance, and you're going to have class 1, class 2, class 3. There's even, I believe, class 4 fan is really high performance. It's based on the outlet velocity and the maximum static pressure that the fan can generate. So to simplify it, in other words, each class is based on a performance limit below which the centrifugal fan will be physically capable of operating safely at every point in the rating. So although AMCA has defined the operating ranges of the various fan classes, it doesn't tell the manufacturers how to meet the requirement, leaving it up to them to design each fan specifically. So a Class 1 fan is going to be a little bit lower end in terms of the static pressure than a Class 2, and a Class 2 is going to be a little bit lower than a Class 3. So as you go up in fan class, you're going to see that the components will be a little bit heavier duty. The casing may be made of a little bit thicker metal because the fan has to be able to operate at those higher performance, developing more static pressure, which is going to require stronger components. But again, the higher the fan class you go, heavier duty components, it's going to cost a little bit more money. So here's just a quick overview of how the fan classes look in terms of charts. So you have some selection zones here. You can see the outlet velocity and the system static pressure are related to each other. So you wouldn't want to select a centrifugal fan having a discharge velocity which is in excess of the upper limit of the fan class at a given static pressure. And if a fan selection is borderline for a particular fan class, you want to go up to the next size fan to provide yourself some flexibility in case any increases in the static pressure are needed in the field. And then all the way to the right, this is just one fan manufacturer's way of, with their typical fan curve and showing where the different fan classes fall for that particular model. So you'll see as you get into higher static pressures, you're going in a higher fan class, and as you're coming down, you're getting in a lower fan class. And the corresponding outlet velocity is going to increase with as the CFM increases. So just a little overview. So fan arrangements. Centrifugal fan arrangements are described by AMCA. They define the location of the bearings, the drive configuration, shaft arrangement, etc. The arrangement numbers and types are going to vary based on the type of the fan, and the discharge and the rotation of the fans is also categorized in the AMCA standards. So if you look through any type of catalog for a utility or centrifugal blower, you've probably seen these terms floating around, and there's some associated diagrams that go with them. This would be one of the fan arrangement diagrams. So you can see that it's illustrating some of the various fan arrangements. And looking through these images, you can see that there's some differences within each arrangement. The type of the fan drive, the motor location, the number of shaft bearings, and where they're located on the shaft itself, as well as the base size and the arrangement of that. So the arrangement notes that are provided for each different fan arrangement show you what type of motor or drive can even be applied. So for example, if you look at arrangement number 4, that's a direct drive arrangement only, whereas arrangement number 1 can be a belt drive or a direct drive arrangement. So arrangement number 1 has 2 bearings on the shaft, arrangement number 4 has no bearings. So the differences like that are what make up these different arrangements and their different classification. And then I'm sure everybody's also seen when applying a centrifugal blower or utility set fan, these various arrangements indicating the rotation and the discharge position of each fan. So the fan rotation, either clockwise or counterclockwise, as well as the angular position of the discharge are shown. So you'll notice with respect to the angular position that both clockwise and counterclockwise rotation, 360 degrees or 0 degrees is pointing directly up for an upblast discharge. But when looking through, when looking at other arrangements, you'll see that if it's clockwise, so if you look at the top left diagram, CW360, you'll see that where our fan is rotating clockwise, our clockwise angular up arrangement is 45 and the discharge is pointing to the right. But if our rotation is counterclockwise, so if you go to the third line, you'll see that it's 45 degrees, but it's now to the left. So the angles are related to the rotation of the fan. And these are very common diagrams. You'll see these in every fan manufacturer's catalog or every fan manufacturer selection software. Sometimes the manufacturers will even break it down even further by applying specific different model nomenclature to the discharge arrangements. But it's good to be aware of the different arrangements you can have with each particular fan and flexible discharge, because in order to meet the application, sometimes one size doesn't work for every system. So single inlet and double inlet, that has to do with the arrangement of the impeller and the arrangement of the fan housing itself. Single width means the single width fan only has one impeller and there's only suction coming in from one side. Similarly, a double width double inlet means that there's two impellers and there's inlet to each impeller is coming in from both sides. Double width double inlet fans typically going to require a bigger casing, and the width of the casing is going to be double of a single impeller fan, obviously because we have to account for two impellers. Most AHUs with these types of fans are going to have double width double inlet fans because they're higher capacity compared to a single width single inlet fan. And conversely, most utility type fans are single width single inlet because the performance required is somewhat lighter duty usually. So one other thing that we can talk about is the system effects, probably a term that everybody's heard before. But the system effect is going to be an additional pressure that's imposed on the fan system as a result of the inlet and discharge configuration of the ductwork itself. The fan performance that is created of each fan by the manufacturer is based on a standardized test that's outlined in AMCA 210. These tests are usually performed under ideal conditions, which as we know don't exist at the job site. So the testing setup and procedures are designed for ideal inlet and outlet conditions, and these fans are tested in a room which is set up as a laboratory with specialized ductwork. The fan manufacturer guarantees that the catalog data obtained through the tests, but will not guarantee the performance when it's installed differently in the field, because obviously the field is not an ideal condition. So the manufacturer will only guarantee that a fan will perform in a standard laboratory arrangement. So as a design engineer, you have to be cognizant of system effects and how they're going to affect the real performance of the fan. So system effect factors, they're published data in AMCA publication 201. There are correction factors based on the different inlet configurations and different outlet configurations, and the shape of the duct connection and even the location of its fitting, where it is in relation to the inlet and the discharge. It's all going to have an effect on the performance of the fan. So anything you place in close proximity to the fan, inlet or discharge, like an elbow or transition, damper, etc., it's all going to have a negative effect on the performance of the fan, and that is what we're referring to when we talk about the system effect. And again, the system effect it's going to have a negative impact on the fan, and it's going to result when you have an obstruction or too close to the inlet or too close to the discharge. So there are curves that are published in these handbooks, which can be referred to, and with these curves, there are different diagrams illustrating what the obstruction is, where the obstruction is, how close it is in relation to the fan itself, and there's a chart that relates this, and based on what obstruction you actually have, you would go to the chart and it would give you a resulting increase in static pressure, which you would have to then apply to your static pressure calc and account for when selecting the fan. So the system effects can decrease the performance of the fan. If you have a fan selection, again, that's based on an ideal condition in the lab and you don't account for the system effect, and your ductwork, when you get into the field, your ductwork is totally elbows everywhere and close to the inlet, close to the outlet, it's going to really reduce the performance of the fan. So you're not going to be able to even, through your fan law, maybe adjust to reach those if your system effect is bad enough. It's going to require a lot more energy to achieve the fan performance. So, again, going back to just our fan law and our system curve example, right? Based on an increase in static pressure, our fan horsepower went from 4.59 all the way up to 6.3. So it's an additional 1.71 horsepower, 746 watts per horsepower, and let's say the fan's operating for 2,100 hours per year. That additional horsepower watts you're going to use as a result of an increase in static pressure is going to add up real quick on the dollar side, on the electric bill side. So, but conversely, if we had taken the system effect into account, we could have maybe selected a fan that's a little bit more efficient for the actual application. So there are some additional result would be excessive vibration, which can happen as a result of the system effect, and as well as excessive noise. And three most common causes of fans not operating properly are non-uniform inlet flow or a swirl at the inlet. So if you have a really abrupt transition, or maybe you have a duct dropping down vertically and you're just kind of tapping into the side of it, those are all arrangements which can create some real turbulent flow with the inlet to the fan, which is going to have a negative effect on the performance. And again, here's just a CFD model of the actual fan, an actual centrifugal fan. Again, the inlet fan going into the impeller and then coming out of the discharge. And then just a housed fan velocity profile. So if you notice, if you remember back to fluid dynamics classes, right, it takes the flow a little while to get developed into a uniform profile. So if we have an obstruction right at the outlet of our fan, where all the pressure and all the velocity is being developed, it's going to have a pretty large negative impact, because you're not dealing with fully developed flow. You're going to take, if you put an obstruction right at of the fan where that red arrow is pointing, you're going to be taking a pretty big hit on your performance of the fan. So as part of the system effect calculations, there's a way to determine the effective duct length, which is where your fan is developing a uniform profile, and that would be the closest you would want to put an obstruction to that particular fan. And just some examples of some interesting duct configurations, which are probably going to affect the system negatively. You can see in this case, the image on the right, we have a blast fan with blast utility set fan with an elbow right at the outlet, and a couple of really abrupt transitions on the inlet of the fan itself. So that's not going to do us any favors when it comes to getting the airflow that we need. And then lastly, just to touch on this real quick, standard CFM and actual CFM. So standard CFM is standard cubic feet per minute, and it's air at the standard air density, or the CFM at the standard air density. And actual cubic feet per minute is going to take into account changes with the density of air. So if different temperatures, different elevations, it's going to have an effect on the actual airflow the fan is going to produce. And so just if you were designing a fan for a higher temperature air or an exhaust at different altitude, you would see that your actual CFM would differ from your calculation with the standard CFM. So you can adjust for that using this particular equation. And with that being said, I think that's going to wrap it up. Ben, I guess we can open it up.
Yeah, Steve, that was excellent. We appreciate it. For everyone out there, I apologize for the audio. We do our best we can. We have practice sessions, but some things are out of our control sometimes. So we will see what we can do, maybe providing this information via email or other ways. The recording will go up on YouTube, but we'll do the best we can. So Steve, we do have a lot of questions. So thank you for everybody sending questions. I'm going to pick a few, and then any we don't get to, I can connect those people with you, and maybe you can help answer some of their questions offline. So we have a question from Lou Garavito on fans. Should you be sizing for part loads or always at full load, or how do you take into consideration sizing for your static pressure at full static pressure and CFM at full load versus considerations for at part load?
That's a good question. So, I mean, yeah, at least the way I approach it is, you know what ultimately your design condition is going to be, right? So your design worst case condition is going to be your full load condition. So ultimately your fan, if you're going to ever be operating at that point, you have to look at that as your worst case. But what you're seeing now a lot is, if you look at some of the selections you'll get from equipment manufacturers, or even if you use their software, there is the option to look at fan curves at varying speeds. So now with everything being, VAV or having variable speed fans, you can also look at how your fan's going to perform over a range of different speeds. So you'll have multiple RPM curves, which would be representative of where your fan is operating at, let's say 10 hertz or 30 hertz or 60 hertz on your VFD. So you can also look at that and use those curves as a tool to help you pick a fan that is still going to meet your ultimate design condition, but also perform over the full range of your maximum and your minimum airflow.
Mm-hmm. And we have a question from Gail Keefe. So thank you, Gail. That kind of ties into this topic. So Gail asks, what is the advantage of overspeeding a fan? I see manufacturers overspeed up to 75 hertz. What happens to the current performance, and what is the reason that you might see that happen?
So this was explained to me, and I apologize because typically we try not to do that. But you're going to have some, you're going to have some factor on your motor, right? So you're going to have a service factor on your motor, which is going to allow you to go over the rated 60 hertz of the motor. Typically, I don't think I would recommend doing that. I mean, I would, I would think it would put a lot of stress on your motor and on the drive. I apologize. I really don't have a lot of experience with that because I would think if the fan and the motor specifically is designed to operate at 60 hertz, it'd probably be a good practice to try to keep it at or below that. I can try to dig up some additional information on that for you. And
yeah, maybe we could do that as a follow-up. So we have another question from Greg Jimenez. So thank you, Greg. Are you seeing an increased request for smoke extractor fans, as an example, operating at a high temperature of, say, 250 degrees Celsius for 2 hours? Or are there any considerations people need to think about when selecting a fan for, say, smoke purge or smoke control or other high temperature application?
I think that's hard to quantify. I definitely you would want the fan to meet the UL listing, but I think you got to look at it as from a good design practice. Yeah, if that fan's going to be an active smoke purge system and it's going to be generating or exhausting smoke and heat, you're going to want to look at that as an extreme case. Because again, you're not definitely in that case not going to be operating at a standard air condition. You're going to be operating well beyond that. So I think it's from a good perspective, good practice. You should definitely be looking at those fans when selecting them for an elevated temperature application.
Yeah, as you were going through your presentation, I was just kind of jotting down all the different things that you need to take into consideration for good design practice when you're selecting fans, whether it's considering your fan laws, velocity, the type, the class, the static pressure, efficiency, service and maintenance, redundancy, curves, voltage, system effect, air density, all these different things to make sure that you're doing it correctly. And I would imagine that the temperature you're operating at is another one of those factors to consider with the manufacturers. Wow, we're getting even more questions here. Let's see here. Do you have a good rule of thumb? This is from Greg Rath on the ASHRAE board. Is there a good rule of thumb for calculating your static pressure requirements based off duct length instead of doing a major point-to-point analysis? So if you're in, say, concept or schematic design, is there a good rule of thumb for various types of systems to determine your static pressure, or that you utilize?
I'm going to be very honest with you. I typically try not to do that. I think once you do the calculations out, I would suggest this. I would take a look at what you have, and then just look at what you think the static pressure would be. So maybe you look at it and you do okay, maybe I have the entire length, right? And then I do a 1.5 times the length allowance for fittings, dampers, etc. And then 1.5 or 2, the total duct length. That seems to me to be like a typical rule of thumb. But do that and then go back and do an actual calculation. And I think the results may surprise you. And it's not even typical for every instance. In some cases, you may be way below that. In other cases, you may be way above that. Each system in itself is so different. And I know everybody's under pressure. Hey, we got to get the job out. We got to get the job done. There's no time to do that. There's no time to do that. But no matter which way you slice it, the right thing to do is really to go through it in that detail, because if you go through it in detail and you have the backup to say, hey, I went through this static pressure calculation, here's what we assume, here's where we're at least you have something to fall back on. If you don't have that calculation, that documentation, if something really goes awry in the field or somebody really changes something, it's kind of, well, we just assume this, and then you really don't have a leg to stand on. So, I just think from a good practice perspective, a good design perspective, being an engineer, it's just a good methodology to go through the exercise, do it right. And it's not a step I would think you'd want to skip because it's so important ultimately to the fan selection and the ultimate performance of the system.
Yeah, I agree. If you're just trying to do some basic selections at the beginning to get some pricing, real early on, it's probably fine. But going any further than that's probably not the the best thing to do. Let's see here. I got a question from Michael Fulton. Are there some cases where a direct drive fan would perform well but should not be specified due to code or any NFPA restrictions? Or is there any time where you would not recommend specifying a direct drive fan?
I don't think there's anything really out there that would prevent you from doing it. I know even now, like some kitchen exhaust fans are even direct drive because as long as you can keep the motor out of the airstream. So I believe that you should use a direct drive fan whenever you possibly can, just because of the efficiency and the simplicity of it. Are there some applications out there that it may or may not be better? Again, if the motor's in the airstream, then you may want to be consideration of what's actually in the airstream. If you have an application maybe where you're exhausting something that's maybe not by the letter of the code, it's a little bit corrosive or rough air, dirty air. But it could have an effect on the motor itself if the motor's in the airstream. You probably would want to be mindful of that. But in terms of how to apply it, I would think if you have the opportunity, a direct drive fan is good, because a direct drive fan can also give you a few more things that a belt drive fan can, right? You could have direct speed control, through a speed controller, whether it's a dial or an ECM motor or something to that effect. Whereas if you needed to make a change in the field, you can just turn the dial. Whereas if you had a belt drive fan, right, you gotta change the pulley, or you gotta adjust the drive, the sheaves or so. Sorry for the long-winded response, but if you have the ability to, I would think a direct drive fan should be the preferred fan, unless there's really a reason why you shouldn't.
Okay. Well, it's 1 o'clock, so we're going to end the presentation. Steve, thank you so much. We do have a lot of questions still here, so I will try to consolidate these maybe in an email to Steve and see if we can get some of these answers out to you. If Steve would be willing to help answer some of these. Make sure to check out our website for any future events, and this will be posted on YouTube, and make sure you fill out the survey when you click out of this webinar so you can get your PDH. So Steve, thank you very much.
Yeah, thanks everybody for tuning in. I appreciate it, and hope everybody stays well and enjoy your long weekend.
All right, have a good one.
Okay, thanks.